Welcome to Study Loop.
For this problem on the topic of waves and sound, we are given the cross-sectional area and the linear density of a copper wire that is strung between two walls. We also know the speed that a transverse wave will travel through this wire at ambient temperature, and we are also given the coefficient of linear expansion for copper as well as Young's modulus for copper. We want to know the speed of the wave when the temperature is lowered by 14 Celsius degrees. Now, we know the tension in the wire initially, we'll call it F0, is given by the equation m over L, the mass per unit length, or the linear mass density of the wire, divided by the speed of the transverse wave squared, v squared. And this is 9.8 times 10 to the minus 3 kilograms per meter times the speed of the transverse wave, 46 meters per second, and that's squared. So we get the original tension, the initial tension in the wire, to be 21 newtons. Now, as the temperature is lowered, the wire will attempt to shrink by an amount delta L, where delta L is equal to alpha times L times delta T, where alpha is the coefficient of thermal expansion. Now, since the wire cannot shrink, a stress will develop according to the following equation. So the stress will be equal to Young's modulus Y times the change in length delta L over the original length L, which we can write as Y times alpha times the change in temperature delta T. Now, this stress corresponds to an additional tension, and the additional tension we'll call F prime is equal to this stress times the area A. And we know that we can write this as Y times this cross-sectional area A times alpha delta T. And we can calculate this additional tension. So this is Young's modulus for copper is 1.1 times 10 to the 11 pascals times the cross-sectional area 1.1 times 10 to the minus 6 meters squared times the coefficient of thermal expansion for copper is 17 times 10 to the minus 6 per Celsius degrees times the change in temperature of 14 Celsius degrees. And so if we calculate, we get the additional friction, or the additional tension, to be 29 newtons. So now the total tension in the wire at the low temperature is F. And the total tension F is equal to the original tension F0 plus this added tension F prime. So the new speed of the wave on the wire, V, is equal to the square root of this new tension F0 plus F prime over the mass per unit length of the wire, m over L. And so since these values are known, we can now find the speed of the transverse wave on the wire at this lower temperature by substituting these values. So that's 21 newtons plus 29 newtons all over the mass per unit length of 9.8 times 10 to the minus 3 kg per meter. And all of this under the square root sign. So calculating, we get the speed of the waves on the wire to now be 71 meters per second.